Hi there, this is Dr. John, your physics and math professor, coming to you with another introductory video to trig functions. Today we're going to look at and try to understand where we get the names of sine, cosine, and tangent, and what those mean, sort of defining them here with this circle. And in a previous video we talked about how the Greeks loved circles and triangles, especially putting right angle triangles inside of circles and seeing what resulted of that. They considered those things of cosmic importance. So here we put a triangle. I'll try to put this triangle here. Let me just read it out for you a little bit. This triangle right here. It's a right angle triangle, as you can see here. It's a right angle triangle right inside of the circle. And what I've drawn here for you is a unit circle. This unit circle has the origin right here at 0, 0. This is your x-axis and your y-axis. And the circle goes till y is equal to 1, x equals to 1, and you've made a circle. Basically, you made a circle with radius 1. The equation of that would be x squared plus y squared is equal to 1 squared, or just 1. You don't need to know this. You just need to know this is what a unit circle looks like. We're going to find this extremely useful in understanding trig functions and how to calculate them. So here we have this triangle set inside this unit circle. I'm just going to erase these red lines so there's not too many lines here for confusion. There we go. I've erased those red lines, and here we have this triangle, as I said. And this is, as you can see, a right angle triangle, and it's the angle theta that I'm concerned about here. So consider a couple of things about this angle here. First of all, this angle, if we wanted to find the sine of that angle, so the sine of theta, it would be equal to the opposite, which is this value right here. This would be the opposite right there, which is the y component right here. Notice it's the y component right here. That would be the sine of theta is the y component divided by the length of the hypotenuse. This is the hypotenuse. But remember, we talked about that this is a unit circle. The radius is 1, so that the hypotenuse is equal to 1. So it's y over 1. You don't need the over 1. So that on a unit circle, the sine of this angle is equal to the y component. And similarly, the cosine of this angle theta is equal to this component right here. It's the x component because that's the adjacent over the hypotenuse. So it's x over 1, or just x. I'm going to try to write that in here maybe a little bit smaller so we have it right here. So here I've rewritten this here very carefully and a little bit smaller. This value here has an x and y value. The x value is the cosine of this angle, and the y value is the sine of this angle. That only applies if the radius here, or the hypotenuse, is equal to 1. That's a unit circle, which we're going to find extremely useful in the future. So now we've got this here. What would the tangent be? Remember, we said before that the tangent is sine over cosine. Well, in this case, the sine is the y, the cosine is the x. So the tangent of this angle theta would be equal to y over x. Or this is the rise up to here, and this is the run. So this would be the slope of this line. Slope of that line right there, of that blue line. That would be the tangent value. I'm going to use this green marker here to draw the tangent line. So this line here hits this point at only one, hits this circle here at only one point, and that's that point right there. So we call this the tangent because a line can be drawn that touches that point right there. Now the slope of this line here is not the same as the tangent. It's related to it, it's tied to it. And actually it's this upside down with a negative. So it's going to be negative x over y. So for example, let's say this slope here of this thing here, of this tangent, is equal to 2. Let's say the rise is 2 and the run is 1. So if this slope here is 2, for example, then this slope over here of this line here would have to be negative, because notice this is positive. The green line would have to be negative. In that case, the slope would be 1/2, but it's negative. And I'll just illustrate that for you over here in just a second. If you notice over here, I've drawn a simple x and y axis. And the x point here is 1, the y point is 2. So the rise is 2, the run is 1. So the slope here is going to be equal to the rise over the run, which is 2 over 1, which is equal to 2, the slope of this line. Now if we wanted a line that was 90 degrees to this, it would be at an angle like this, right here. Notice how it would have a run of 2 and a rise of -1. So the slope of this one would be the rise, 1 over 2, there's a minus sign, so it would be -1/2. So it's the slope of perpendicular lines, the slopes are flipped and a negative sign. Simple as that. So we do that over here too. So the slope of this thing here, the blue line, is actually the tangent. But the green line, which intersects this thing and forms a tangent to the circle, is related to the slope of this and is related to the tangent of this angle in this way. It's the negative and flipped. So you might say it's the negative cotangent if you want to. We'll be looking at that in a second. So this sort of gives us an explanation of where we get the tangent function from. Now what about the sine function? Let me erase a couple of things here and I'm going to illustrate that for you. All right, I've erased a bunch of the extra lines over here and drawn this new circle over here to sort of show this bigger circle, this dashed line circle. I've just drawn a little smaller, a complete circle over here. And I wanted to explain something to you about how we get the word sine. And if you take a look at this pink line here, I'm going to sort of redraw this here. Draw this pink line right here. And then I'm going to draw the x-axis just like this all the way through it. And this one over here. This is like the x and the y-axis. And this is this pink line right here, drawn right through it. And the triangle that we had was like this. So this is duplicating this triangle over here. So notice this line over here actually cuts this circle at 2 points, this point and that point. And it's the internal line that cuts a circle at 2 points. That has a name in geometry that we call a chord. And it's spelled like this. It's C-H-O-R-D. This is not the same as a chord like this, C-O-R-D. C-O-R-D would be a length of rope, a cord of rope that you might use to tie something up. This is a chord, which is a line from one part in a circle to another part in a circle that cuts the circle like that. And just in case you're interested, if the circle keeps going outside, this is called a secant. The same thing, it's a chord when it's on the inside. It's a secant if it continues on the outside. We're not concerned about that right now, so I'm just going to erase that part. So this piece here, you can see that this sine piece here is this piece right here, and it would form half of this chord of a circle. And we had a word many years ago in the Sanskrit language, which was the word that they thought was chord. It was translated into Latin, mistranslated into Latin, and then translated from Latin into English, and we have the word sine. So it goes something like this. So we had a word many years ago that people thought meant chord of a circle. It was mistranslated, poorly translated into Latin to be the word sine, and then translated into English from there, where we get our word sine, S-I-N-E. So that's how we get the idea of sine, which is a chord of a circle. Notice the cosine, which is this piece here, can't really form a chord of a circle because it doesn't go right to the edge. I don't know if that helps you or not, but gives you an idea where we get the word sine from. It's sort of a mistranslation from another language or from a couple of other languages. Now we're going to look briefly at where we get the word cosine. I'm going to erase a couple of things and come back to you. Okay, I'm back. I've erased some more of the mess over here and redrawn this triangle up here, giving it this angle theta and also another angle alpha over there. And remember we said that the sine of angle theta is equal to, here's the angle theta, the opposite over the hypotenuse, B over C. But if you look at the cosine here, the cosine of angle alpha over there, cosine of angle alpha is the adjacent B over the hypotenuse C. Notice that the sine of angle theta is the same as the cosine of angle alpha. And the ancient Greeks, when they were studying triangles, they found out that all the inside angles to a triangle added up to 180. And since this one was 90 degrees, that meant these two, alpha and theta. So alpha plus theta had to add up to 90 degrees as well. And because 90 degrees was considered to be very complete or beautiful, they said that these two completed each other. They were complementary. I'm going to write that word out here for you. These angles were complementary to each other. That is, they added up to 90 degrees. So any two angles that add up to 90 degrees are considered complementary angles, like 20 and 70. Those are complementary angles. 45 and 45 would be complementary angles. and 30 and 60. Of course, you have many other examples. These are all considered complementary angles. And if they add up to 90 degrees, that's considered to be extremely beautiful. It's almost like they belong together. It's like a love story between two people. They belong to each other. They complement each other. Now, this is not the same word as a complement. A compliment, with an I here, is a nice thing that one person says about another thing. It's a compliment. This thing here, though, to complement means to complete something. So alpha completes theta to make it 90 degrees. Now, that's where we actually get this little CO from. The CO is where we have this thing in the cosine. The cosine is a function that complements the sine. This would be how you would fully write out the cosine function. It's the complementary sine function, or the co-sine function. In other words, this function completes this function. So inside of a triangle, let's say a right angle triangle like this, if you have this angle alpha and this angle theta here, and we have the sine of this, it's going to be the same as the cosine of this because they complement each other. Let's say I wanted to take, I knew what the sine of theta, this one right here, is b over c. So that's this one over this one here. And the cosine of this is also b over c. So we could write this out this way. If we would say, I want the complementary sine of the complementary angle to theta, which is the complementary theta. So here, the complementary sine would be the cosine. The complementary theta would be alpha. So notice here, I have a complementary here and a complementary here. Those two, like two negatives, sort of cancel each other out, and you're just left with sine theta. So all of this would mean this is the same as sine theta. The complementary angle is alpha, and the complementary function is cosine. So you can actually work back and forth between sines and cosines. I'll give you a couple of quick examples. The sine of 30 degrees would be equal to the cosine of 60 degrees, because these are complementary angles. Those are complementary functions. Or if you want to use the other things that we've had as well that I've introduced to you, the cotangent of 20 degrees is going to be the same as the tangent of 70 degrees. Or if I want to use the reciprocal functions, I would say the cosecant. Remember the abbreviations for that is CSC of 15 degrees is the same as the secant of what? 75. 75 plus this is 80, that's 90. So you can use any of these functions. Let me write these functions out for you and just explain one more thing, and then we'll be done with this video. Here I've written up the regular trig functions, sine, cosine, and tangent. Those are the ones you can use a lot. And then the ones that are in the denominator, the reciprocal, the upside down, the cosecant, the secant, and the cotangent. If you remember, this here stands for 1 over the sine. This stands for 1 over the cosine. This stands for 1 over the tangent. So they're flips of this. But notice here, here's a big confusing thing. Notice this one is the sine and this one has the co-function. But this one is the regular secant and this one has the co in front of it. So you would think if they were going to be symmetrical, or if there was going to be some way of memorizing it, this would have the co-function in front of it. But it doesn't. It's a little bit confusing, and maybe it's a little bit hard to memorize. You just have to realize that the secant belongs to the cosine and the cosecant belongs to the sine, even though the cos are on the opposite ones. In another video, I'm going to explain where we get this here, the secant, where we get that name. The cosecant, that is the complementary to the secant, just like this is to this. And in a way, this one is complementary to this one too, so you can go back and forth on that. This one here, the cotangent, it is a reciprocal of this, but it is also the complementary function to the tangent. It's both at the same time. So this one serves a dual purpose. So in another video, I'm going to explain this. Hopefully in this video, it helped you to see how we get the sine, the name sine, as we get it from a chord that intersects a circle. The cosine comes from being the complementary function, and the tangent comes from being related to the tangent of the point on the unit circle where that touches. I hope that helps. If it does, like and subscribe. I will see you in another video. Bye-bye.